Hello everyone, this is Ketisha. In this video, I'm going to go through question number 9 and 10 from the AQA Physics paper 1 higher tier. This is the specimen paper. Question number 9 is on this atomic structure, mainly to do with radioactive decay. A student models the random nature of radioactive decay by using 100 die. He rolls the die and removes any that land with the number 6 facing upwards. He rolls the remaining die again. The student repeats this process a number of times. So we've got table 1 showing his results. So the first roll, all of them, number of die remaining is 100, and then it reduces every single time. He rolls it. Give 2 reasons why this is a good model for the random nature of radioactive decay. Now, every single time a die lands on 6, he's not putting it back, he's actually removing it. That's why the total number is actually going down every single time he's actually rolling the die. Why is this a good model for the random nature of radioactive decay? Well, you can't predict which die is going to land on 6, which means that is a totally random event. So you cannot predict which die or atom will decay here, and you cannot predict when a die or an atom will also decay. The student's results are shown in figure 11. So you've got starting at 100 and the number of die remaining, and the number of rolls is on the x-axis, and the line goes steadily down. So use figure 11 to determine the half-life of these die using this model. Show on figure 11 how you work out your answer. So you need to make sure that you have evidence of this on the graph. How do you work out the half-life? The half-life is worked out by looking at, okay, the number of die remaining is 100, so half that number is going to be 50. So if I draw a line straight from 50, right, and then drop that down, and that's 3.6. So that would be 3.6 rolls. A teacher uses a protactinium or generator to produce a sample of radioactive material that has a half-life of 70 seconds. In the first stage of the protactinium generator, uranium decays into thorium and alpha radiation is emitted. The decay can be represented by the equation shown in figure 12. So that's uranium-238, that's the mass number on the top, and the proton number, which is 92. And we need to fill in what's in the box. But to do that, you need to know information about the alpha particle. Remember, an alpha particle is also a helium nucleus. A helium nucleus has 2 protons, which is basically that bottom number is a proton number, and it also has 2 neutrons. No electrons, because we are talking only about the nucleus. Hence, the total mass of this is 4. So 4 and 2, you need to add these numbers, and the top numbers should add up to the mass of the uranium. You're breaking the uranium into 2, right? One of that is a thorium and the other part is the alpha, so you can't lose mass in between. So what is the proton number of thorium? Well, 92 minus 2 should be 90. The answer is 90. When protactinium decays, a new element is formed and radiation is emitted. The decay can be represented by the equation shown in figure 13. So you've got protactinium-234 decaying into an element X plus radiation is given. Now, what is actually happening to the mass? The mass is actually remaining the same. It's here. What is happening to the proton number? proton number is actually increasing by 1. Right? Now, what type of radiation will actually give out will cause the proton number to increase, but the mass number to remain the same. When protactinium decays, a new element X is formed. Use information from figure 12 and 13 to determine the name of element X. Now, we are looking at the proton number. That's the important thing, because you're not going to get a periodic table for the physics paper. So the proton number is what decides what type of element it is. So if Pa is protactinium, what would be 92? Now the clue is actually in the question. Use figure 12 and 13. So let's have a look at 12 and 13. Does it give any clue? Yes. If it's 92, then it has to be uranium. Uranium always has 92 protons. If it is 90 protons, it is thorium. 91 is protactinium. So the element X is uranium. And by the way, the radiation that can cause this to happen is beta radiation. Remember, beta is actually an electron with a mass of 0, but it has charge of -1. Okay, question 9.5 actually asks that. Determine the type of radiation emitted as protactinium decays into a new element. Give a reason for your answer. The type of radiation is beta. The reason is the proton number has actually gone up by 1. Why would that happen? The proton number has gone up by 1, right? By 1 as an electron, as a neutron. A neutron decays to proton and an electron. Question 9.6. The teacher wears polythene gloves as a safety precaution when handling radioactive materials. The polythene gloves do not stop the teacher's hands from being irradiated, meaning that it might not stop the radiation going through the polythene glove and going into the skin. It might actually stop the alpha particles, but definitely won't stop the beta or the gamma. Explain why the teacher wears the polythene gloves. The main reason is to prevent contamination. What does contamination mean? Is to make sure that you don't actually get any of the dust particles or any of the radioactive material on your hands. So, prevents contamination, or you could say it prevents transfer of radioactive material to the teacher's hands. Right? The second mark is actually to say which could cause damage because irradiation over a longer period of time. Because radiation is dangerous. It is ionizing radiation. If it's alpha or beta, by wearing a polythene glove, we can prevent the contamination from the sample. Question number 10 is on atomic structure again. Electricity is generated in a nuclear power station. Fission is a process by which energy is released in the nuclear reactor. Figure 14 shows the first part of the nuclear fission reaction. Complete figure 14 to show how fission processes start a chain reaction. Now, a neutron is fired at an unstable nucleus, usually polonium or uranium. Now, the word when we say fire doesn't mean that it's actually going fast. The uranium actually needs to be slow in order for it to go and be absorbed by the nucleus. Right? Now, they're asking for a diagram. So, once that neutron goes into the nucleus, that nucleus splits up into two daughter nuclei. and it also produces 2 to 3, right? Generally 3, but 2 is fine as well. 3 neutrons. And 2 daughter nuclei. Now the daughter nuclei you don't really need to know, because that is not important for the fission reaction. It's these 3 neutrons, what they actually do. Each of these 3 neutrons can actually go and break up another unstable nuclei, right? So as you can see, one neutron can break one nucleus, and from the resulting 3 neutrons, 3 neutrons can actually they can break down 3 different unstable nuclei, and each of them can actually break down further. Now this is what we call a chain reaction. So an image like this is actually going to give you all 3 marks. You don't have to draw too many of them. Figure 15 shows the inside of a nuclear reactor in a nuclear power station. So you have the container, which is basically the protective layer outside, and the cold water is pumped from the bottom. And as the water goes through, the water gets heated up because of the nuclear reaction, and the hot water is pumped out, and that's actually more like steam that comes out. Now, the nuclear rods are basically these dark rods, and in between you have these control rods. Now the control rods are usually graphite rods. Now what does the graphite rods actually do? Now during the course of the nuclear fission reaction, you're going to get these free neutrons that is actually released, and those free neutrons, when they come into the fuel rod, they are going to break down more and release more. By having the nuclear control rods in between, if you insert them, they will absorb the free neutrons, thereby slowing down the chain reaction. So the question actually gives part of it. In a nuclear reactor, a chain reaction occurs which causes neutrons to be released. The control rods absorb the neutrons. The control rods can be moved up or down. Explain how the energy released by the chain reaction is affected by moving the control rods. Now, if you move the control rods, you're going to absorb the neutrons. That means you're slowing down the chain reaction, so you're lowering the energy production. If you lift it up, then there's more free neutrons for the chain reaction to take place. So lowering the control rod increases the number of neutrons absorbed, so energy released decreases. Figure 16 shows how the power output from the nuclear reactor would change if the control rods were removed. So if you remove the control rods within about 12 minutes, right, the power output is going to go from about 600 megawatt to more than 2500. So all you need is less than 12 minutes for it to go out of hand, because the chain reaction is quite fast. Calculate the rate of increase of power output at 10 minutes. At 10 minutes, which is here, and that's over there. So let's see, that's about 6.5 boxes. So between 6.5 boxes there. So let me draw a line. So each box, so that's 400, 0 to 400. So if I divide 400 by 10, that's 40. So that's about 5, 6, 7. 40 times 7 is 240. Am I right? So no, that's 280. Okay. 280. So I need to add plus another 280. 280 to 1200. So about 1480 divided by 10 gives me around 1400 and no 148. So that's about 148 megawatts per minute. I think this is correct because the marking scheme, however, if you were to download the marking scheme, it says rate of increase is between 240 to 276 megawatt per minute, but that cannot be because at 10 minutes is definitely less than 1600. So even if I divide 1600 by 10, that's 160 megawatts. So my answer is correct because for it to be between 240, we are looking at the graph, which is at 12 minutes. So I think there's an error in the marking scheme, unless I am wrong somewhere. If I am, let me know in the comments and I appreciate your feedback. Thanks for watching and I will see you in the next video. I made a mistake. This paper has 13 questions, which means there's 3 more questions to go and I will make one last video to go through all 3 questions. Thanks for watching again. I will see you in the next video.